All right, so Bitcoin is a blockchain, so it consists of blocks. So let's look at what is inside these blocks. Okay, so our topic is now Bitcoin blocks. So as you can see, in a block, we have some headers and some block data. So transactions are recorded here by the miners. And the zero transaction, the initial one, is actually the transaction where the miner rewards themselves. Okay, so in this transaction zero in Bitcoin, there is no input because you are not transferring money from anywhere, but there is the output where you reward yourself with Bitcoin. Initially, it was 50, but it was halved in every 4 years. So currently miners get 6.25, but it will be halved again in a few years. So the remaining transactions are the transactions you heard from other people where they transferring Bitcoin to some other people. So actually you don't have to wait to hear any transactions. So in some alternative coins, initially, since people don't have any coins and don't transfer them, the first thousands of blocks actually contain only this reward transaction. Okay, the others actually don't exist. So the first few blocks of Bitcoin also like this. Because since nobody have any Bitcoin, you cannot transfer it to some other people. But when you have more than one transaction, what you do is to create a Merkle tree. So you take the hashes of these transactions, okay? Then in pairs, you also keep hashing them. And at the end, you get a single hash, which is referred to as Merkle root. So if you change any of the transactions here, it also changes the Merkle root. But the good thing is that if you want to check if this transaction is in this block, you don't need to, as a light node, you don't need all of these transactions or the hashes, for instance. You all need this transaction, this hash value, this hash value. You calculate it, and also you need this hash value to check the Merkle root. Okay, you don't need to know the remaining ones. This allows some speed in light nodes. So as I mentioned, we have the block headers and block data. So first, let's look at what is in these headers and what is the block data. So block structure is as follows. You first write the block size in 4 bytes. You have the block header, 80 bytes. Number of transactions, it varies between 1 to 9 bytes. And the transactions. First transaction, as I mentioned, is the transaction where the miner award Bitcoin to themselves, which is referred to as coin-based transaction. Okay, so we said that the header is 80 bytes. Let's look at what this 80 bytes consists of. So it starts with the version. So in 4 bytes, you write the version. I will explain all of them in detail in the following slides. But the important thing is that you write it as little ending. This is important because we will see that some other data are written in some other encoding. Okay, for instance, this is the previous block hash, 32 bytes. In other words, 256 bits. As you can see, we are using SHA-256 here, but you write it in the internal byte order. Okay, you write the Merkle root. Again, it is a hash output. Then you write the timestamp, this classic Unix timestamp, but it is also in little endian. Difficulty target, this is the target that the miner tries to obtain a hash value that is less than this target. Okay, so since there is a target and you are trying to obtain a value that is less than this value, in bit representation, this means that the solution of the miner starts with many 0 bits. Okay. And finally, we have a nonce value, which is 4 bytes, which is 32 bits, where miners, modify it to solve the puzzle. But of course, nowadays, it is not enough because if you try every nonce, most probably you wouldn't solve it. So you have to change something else, which we will talk about in mining. But you can, modify the stuff in your coin-based transaction so that you can, continue mining with different data. So let's start with Bitcoin header. So the first value is version number to track software and protocol upgrades. So if you provide a new upgrade, which will be effective maybe months later, you can see how many of the miners actually updated their software by looking at the version number of this, okay? Because it is written by the miner who solved the mining puzzle. Previous block hash, hash of the previous block header. You might think that since this is not the hash of the whole data, so maybe it doesn't provide enough integrity, but since the header contains the Merkle root, any change in the transactions will modify the Merkle root in the header, so it will also change the hash here. So it is enough to take the hash of the previous block header. Timestamp the moment the successful miner starting hashing the header. Difficulty target, the encoded version of the maximum value that the block's header hash must be less than or equal to. Nonce, 32-bit value miners can choose. As you can see, these are the block header, which takes 80 bytes. Okay. So let's talk about them in detail. The Bitcoin version. Version number is to track software and protocol upgrades, indicates which set of block validation rules to follow. For instance, the version first one is Genesis block. Since the Genesis block, the version number is 1, which started in 2009. Then Bitcoin Core 0.7.0 in September 2012 provided the soft fork. So the version became 2. Required block height parameter to be recorded in Coinbase. So this is the BIP34 upgrade. With Bitcoin Core 0.10.0 in February 2015, this is also a soft fork, and it is BIP66. Requires strict DAR encoding of all elliptic curve digital signature algorithm signatures in new blocks. Bitcoin Core version 0.11.2 in November 15, soft fork, which supports the following opcode check log time verify, which is again introduced by BIP, another BIP, which is 65. So a newer method called version bits is being designed to manage future soft forking changes. And for more information, you can see BIP9, which might be effective in the future. So we will see different ways of defining the versions due to this BIP update. Let's look at the previous block hash. Hash of the previous block header, not the hash of the whole block. Chaining the blocks using the previous block's headers hash, hence the name blockchain, provides security. So this way you provide the integrity. This is why we call it tamper evident and tamper resistant, right? An attacker that changes a block in the past has to change every following block until the current one. Timestamp, the moment the successful miner started hashing the header, represented as number of seconds from 1st of January 1970, which is generally used in Unix formatting. But of course, since you start mining and it takes a few minutes to solve it, generally in 10 minutes. So actually, nobody else knows the exact moment you start. So you have some freedom here. You can write 5 seconds later or earlier and so on. Miners sometimes use it to, try to solve the hashing puzzle. Difficulty target, it is the encoded version of the maximum value that the block's header hash must be. So whenever miner solves the problem, every node actually checks if the hash is less than this value. Miners aim to obtain a block header hash that is less than or equal to the difficulty target. Difficulty is updated every 2016 blocks. Since it takes on average 10 minutes to write a block, 2016 blocks actually means 2 weeks. So when a difficulty is determined, it takes 2 weeks to update it, okay? So the formula is something like, actual time of the last 2016 blocks divided by this many minutes, and you multiply with the old difficulty to obtain a new difficulty. But just understand that this is just a, like a pseudo formula. The exact formula is a little bit complicated, and I recommend you to check the Bitcoin implementation. Here, what I'm trying to tell is that, so in general, if everybody is mining with the same speed as the previous blocks, it will take around this many minutes to mine this many blocks, right? So in 2 weeks, if no new miners are added to the system, it will take, on average, this many minutes. But assume that once the new difficulty is determined, let's assume that a lot of new miners are joined to the pool. So it will take now less than 10 minutes to solve this problem. So after this many blocks, which you were expecting to happen in 14 days, but maybe it happened in 10 days because there were new miners. So we had in total larger computational power. So we solved the mining problem faster. So now we have to determine the new difficulty. But the thing is that if more people leave as the miners, then it will take more than 10 minutes for us to solve the problem, right? So new difficulty does not have to be always larger than the old difficulty. This is the thing. So some people think that difficulty always increases. Actually, it can decrease, and it actually decreased in the past, okay? So it is not always getting harder to mine. Sometimes it gets easier because maybe it may not be profitable for some miners. Maybe the electricity bills they pay become larger and the Bitcoin price is low. So they may say that, okay, let's not mine for some time. So this way, difficulty can be smaller than the previous difficulty. So let's talk about nonce. This is 32-bit value. Miners can choose as they wish. Once every nonce is tried, which is very easy because 32-bit means that you can try at most 2 to the 32 different nonce values, which you can do actually less than a second on a GPU, not on an ASIC. On a GPU, you can try all of these nonces in less than a second. This means that ASICs actually try these many nonces in a very fast way. So you have to go back and change the block data so that you can, your input can be different. This is important because I still see many recent documents where they say that miners can only modify these 32-bit values, but it takes less than a second to modify them, and you exhaust all of them. So you have to change the block data where you have the coin base. Once you change it, it changes the hashes until the Merkle root. Now you are allowed to choose all of these nonces again because the Merkle root is not changed. Okay, but we will talk about mining in the future more. Okay, so let's look at the genesis block here. So in hexadecimal, this is the block. So here, as you can see, if you convert it into ASCII, here I'm not decrypting anything, by the way. Some people think that I'm kind of encrypting or decrypting something. I'm simply converting hexadecimal to ASCII characters, okay? Here you can see that there is a message hidden here by Satoshi. The times 3rd of January, and Chancellor on brink of second bailout for banks. So this is the headline of the Times of that day. So here Satoshi is showing that I created this block exactly on this day. This is important because what he could do was as follows. He could start mining like maybe 1 month before this day and announce this block at the 3rd of January, where he already knows the following maybe thousands of blocks which he pre-mined before. So this way he can always provide these blocks in every 10 minutes and showing that he actually competing with other miners, but he actually pre-mined. So here he proves that he didn't pre-mine. Some alternative currencies actually do this deliberately, but here he's proving that he really started mining at this day, but he is also sending a message because this actually about the financial crisis from 2008, and here actually in United States, government use citizen taxes to save the banks. This actually headlines tells this. Okay, actually this is the stance that Satoshi is trying to show. He is trying to show that why we actually trust governments or countries or banks. This is why he's introducing a new cryptocurrency. Okay. So in that, this whole block is also modified like this to show us what it consists. As you can see, the version is 1. The previous block, actually, there doesn't exist any previous block, so it is 0. This is the Merkle root, timestamp nonce. Number of transactions 1 because it only contains a coin base. Here in the script sig, he hides the message, I think, to this part. This, the times headline, and also this is the signature he provides and so on. So we will see transactions in the following slides. So let's talk about more on the Genesis block. So to start the system, somebody has to decide the initial block, right? So Satoshi designed it like this. So he is actually mining himself and obtaining 50 Bitcoins. So Genesis block is hard-coded to the Bitcoin core, so nobody can change it. The software already contains it. By including the New York Times headline from 3rd January 2009, Satoshi proves that they didn't do pre-mining and have no head start. Some other cryptocurrencies were deliberately pre-mined. Many alternative currencies did that. Genesis block's mining reward of 50 Bitcoins was sent to this address. Okay, so we know that this address belongs to Satoshi. So if somebody claims that he is Satoshi, all they need to transfer money from this account to someplace else and show that they have the private key. So the mystery can be solved instantly. So everybody who's claiming that they are Satoshi actually lying because they cannot do this. Okay, that is the whole reason we don't trust people who say that they are Satoshi. Note that actually Satoshi cannot spend this 50 Bitcoins because when a node starts up, it initializes its copy of the block database alongside the Genesis block and then begins the synchronization process. So actually they synchronize with everybody in the network. So they come to the current block and they actually store every Bitcoin that is not spent so far. So this 50 Bitcoin actually hasn't been spent, but in the software, Satoshi didn't include it in the codes. So actually nobody can spend this 50 Bitcoin. So even if he has the private key, trying to send this to somebody else, people using the software will not understand what he's trying to transfer. So for some reason, Satoshi decided not to add the Coinbase transaction from the Genesis block to the global transaction database. So some people think that this is a mistake, a human error. But I think here Satoshi trying to again show that he hasn't have a head start. So he's deliberately actually destroying those 50 Bitcoins, saying that I'm starting at the same time with you. Okay, because once he announced this block, people who knows that that blockchain will be created on the mailing list, they can start with the mining after this announcement so that they can actually get ahead of Satoshi if they wanted. So here again, I believe that Satoshi did this deliberately, saying that he even didn't start with a 50 Bitcoin that he can easily get. Thus, all the nodes in the network will reject the block if somebody tries to spend this 50 Bitcoins. Again, something that it is an oversight, but most probably Satoshi didn't want a head start. This is my personal opinion. So you might think that, a few minutes ago I said that somebody can prove that they are Satoshi by spending it. Now I'm saying that they cannot spend it. Actually, that address received many Bitcoins in the past. Like there are more than 3,000 transactions where people send money to this account. So this is why the total received is not 50 Bitcoins, but larger than 50 Bitcoins. So Satoshi can appear and use this remaining 18 Bitcoins and transfer them to someplace else. This is how Satoshi can prove that he's really Satoshi. Okay, as you can see, this account received this amount of Bitcoin, but nobody sent it to any place else. Right? So this is the catch, actually. All right. So we were talking about Bitcoin blocks. Let's look at the specifications of Bitcoin. So block size is 1 megabyte. Again, it is virtually 4 megabytes since 2017 due to an update here, because the main idea is that initially we were writing all of the signatures on the block. So we were exhausting this 1 megabyte easily. Now we are actually storing them at the end of the block, which is not included. Doesn't count them in this 1 megabyte part. So this way you can actually store more transactions, but with the signatures it can be up to 4 megabytes. Blockchain size, I recorded it a few months ago, so it exceeded 458 gigabytes. As you can see, 14 years of usage and blockchain is still can be stored in a laptop hard drive, which is like around 5 gigabytes if you have that amount of hard drive. But if you're storing in a desktop, we can easily buy 4 or 8 terabytes of hard drive. So this blockchain size, the increase in the size does not cause any problem. But in Ethereum, this might be a problem because it is increasing a little bit faster than the Bitcoin. So maybe in the future, some smart contracts that have never been used will be stored in a different hard drive, and they will be actually checked whenever somebody tries to use them. So most probably servers using as an Ethereum node will keep the blockchain in an SSD, but unused smart contracts will be most probably stored in a traditional hard drive, which has larger storage. Yes, block addition time is 10 minutes. Total Bitcoin amount is 21 million. So there can be at most this many Bitcoins in the market, but in circulation, we have almost a huge part of it, like 19.3 million. Again, as of February, since we are in April now, probably it is 19.4 or maybe a little bit higher. So mining award currently is 6.25 Bitcoins, because it is halved every 4 years. So it started with 50, 4 years later, it became 25 and so on. So in early 2024, we will have another halving, so the reward will be reduced to this. Okay. So these are the main parameters chosen by Satoshi. Right? Instead of 21 million, he could say maybe 200 million, but initially he chose this. So any change in these specifications causes a hard fork. This means that if you change it, people who made those changes will be actually working on a new blockchain now. So you can actually creating two blockchains. You can see them as parallel universes. So any change to these specifications will cause a hard fork. Okay, so people who updated their software and who will not understand each other. But if you make a small change, like adding a new cryptographic algorithm, this only causes a soft fork. So this way you don't have to divide the blockchain into two. And Schnorr signatures is an example to this. Again, we will talk about it when we talk about forks. So investigating Bitcoin data. This is very important for forensics people. So you have to understand what a blockchain block consists of and how you can interpret it. So many services can be used to access cryptocurrency data. So if you are not keeping the blockchain, a copy of the blockchain by yourself, you can simply visit a web page like blockchain.info. For a transaction ID like transaction ID here, you can simply replace it here. And you can see the transaction data in hexadecimal. Of course, if you remove it, you see it in a JSON format and so on. For the Genesis block, for example, you can follow this link and see the transaction. Checking a balance, you can write the wallet address here. This is the address that is used in the Genesis block by Satoshi. You can follow this link and see all of the transactions they received, total amount they have, and how much they spent so far, and so on. If you want to look at the unspent transactions, you can simply write unspent instead of balance, and you can see the unspent cryptocurrencies of that wallet address. But however, forensics investigators should be able to extract the same data from the blockchain itself. Relying on a third-party web page is not a good idea. It wouldn't hold in the court, right? And it wouldn't be fast anyway. You will be limited by your network speed here. If you want to make a lot of checks, it would be better if you have the whole blockchain in your computer.